Hey everyone, in this video we are going to briefly review factoring polynomials based on the ed puzzle you guys watched on Monday, which was difference of squares and sum and difference of cubes. Then we're going to do 4 examples of solving by factoring, and then we're going to talk about division of polynomials, and we will be performing long division and synthetic. So let's get started. To start, we're going to review how to factor a difference of squares problem. Which I like to call DOS, D-O-S, difference of squares. Okay, so for example, I'm going to give us, and the goal is to factor 64x squared minus 100. And something you'll notice is whenever you have a difference of squares, is you have a binomial. You have 2 terms, meaning it's a binomial and it's a perfect square minus a perfect square. And the formula for factoring a difference of squares, it says that a squared minus b squared is equal to a plus b times a minus b. Or really, I like to set it up in this way, is I like to find out what a is, and since it's a perfect square minus a perfect square, I know that a is going to have to be the square root of 64x squared, which is 8x, because the square root of 64 is 8, the square root of x squared is x, and b is going to be the square root of 100. Well, 10 times 10 is 100, so the square root of 100 must be 10. So using my pattern here for the difference of squares, is I just plug in 8x, 10, 8x, 10, and the only difference is I have a plus and a minus in between. So I like to say grab your partners, drop them down, change the signs, it's going down. So our a value, notice it always goes in the first spot. This was 8x, the square root of 64x squared. And my b value is 10. It always goes on the right-hand side. And you will always have a difference of signs between the two. So one of them will always be plus and one of them will be minus. Now, it does not matter which one comes first. It could be minus and plus, but this is the correct factorization of a difference of squares. It's a perfect square minus a perfect square. We have to take the square root of each piece to find our first one and our second one, or our a and our b, and we just follow the pattern accordingly. So let's talk about solving by factoring. And the first one, we're going to deal with a sum of cubes, and then we're going to take it a step further and actually solve for specific values of x. And now we know how to solve. We talked about solving when we talked about quadratics. We'll use the zero product property. But so in this set of problems, we're going to solve by factoring. So it gives us a little bit of factoring review. And it also gives us a little bit of review on solving something, finding a specific value of x. So our first example is going to say solve this equation, right? X to the third plus 125 is equal to 0. Again, I have a binomial equal to 0. Whenever we have things set equal to 0, we know that we have, we're looking for x-intercepts. And this actually is a sum of cubes problem. This is a sum of cubes problem because I have a perfect cube plus a perfect cube. So I know that I can factor the left-hand side by using my sum of cubes formula, which If you remember from the first ed puzzle about the sum of cubes, it's first one, first one squared, first one times the second one squared. Use some soap because you don't want to be nasty, right? So in order to use that, we need to find out what the first one and the second one is. So the first one, or A, is going to be equal to the cube root of the first term, x to the third. The cube root of x to the third is going to just be x, because x times x times x is x to the third. And my second one is going to be the cube root of 125. Now, since 5 times 5 times 5 is 125, that's what that value is going to be. So I end up factoring the left-hand side, x to the third plus 125, as the following. And we're going to sing the jingle to figure it out. Okay? So remember, the jingle goes, first one, second one, first one squared, first one times the second one squared. Use some soap, because you don't want to be nasty. Looking at this sign, we have the same sign, the opposite sign, and always positive. Okay, cleaning it up, I would end up with x 5, x plus 5 as my first factor, times x squared minus 5x, just reorder it, plus 5 times 5 is 25, and set that equal to 0. It's very important that we clean it up. We usually end up putting the second one first, the x term second, and make sure you're squaring these actual values. So what I've done so far is factored x to the third plus 125. That is a sum of cubes. I used my pattern and my jingle to factor it. Now I have it set equal to 0. So this is where the actual solving comes in. Up to now, all we've done is factor. So I have something times something is equal to 0. So we know that by the zero product property, the only way that this product of two polynomials will be equal to 0 is if either the first thing is equal to 0 or the second thing. So I'm going to set both of them equal to 0. This first one is nice and easy because it's a linear term. We subtract 5 and we get x equals -5 as one of my solutions. Now the second one is not so nice. This does not factor. As a matter of fact, this will never factor using the sum of cubes or difference of cubes formula. You will always have to use the quadratic formula. You'll have to use the quadratic formula to find out what this, what x values this gives. So remember, x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And when I plug that in, a is 1, b is -5, c is 25. I get x is equal to opposite b, so opposite of -5 is +5, plus or minus the square root b squared, -5 squared is 25, minus 4 times a is 1, c is 25, all over 2 times 1. Continuing this, I get x is equal to 5 plus or minus the square root of 25 minus 100, so -75 all over 2. Here, whenever we have a negative inside of the square root, we can pull it out by writing it as an imaginary number. It's a complex solution. So we have 5 plus or minus I radical 75 all over 2. But remember, we can break down this radical. Remember that the square root, I guess I'll just do a quick note. Square root of 75 is really like 25 times 3. And 25 is 5 times 5. 5, 10, 15, 20, 25. And so this pair of 2 escapes. So this really becomes 5 radical 3. So x is equal to 5 plus or minus 5i radical 3. This 5, I guess I should have done this. 5i radical 3. This 5 came from breaking down 75. This I came from the negative on the inside, all over 2. And something I want you guys to notice here is this was a degree 3 polynomial, right? X to the third plus 125. And here is one x value. And since we have the plus or minus, here's 2. So I have found 3 solutions in total, both real and complex. 2 of them are complex, 1 of them is real. This 3 solutions, the total number of solutions will always match the degree that we have. So that's a little bit review of sum of cubes. I want to do 3 more examples, and they'll go into various factoring strategies for polynomials that are degree 3 and higher. So this was degree 3. The next few actually are all going to be degree 4 polynomials, and we'll use actually a couple different strategies to factor. So we'll still be solving by factoring, which meaning we're going to have to actually solve them for specific x values. But it won't necessarily be a sum of cubes, difference of cubes, or some difference of squares. I apologize. So example 2 says to solve this by factoring, we're going to have x to the 4th plus 6x squared minus 16 is equal to 0. And the only difference between this degree 4 polynomial and if it was a degree 2 polynomial is that the factors of x to the 4th are no longer x times x, because x times x is only x squared, but it's x squared times x squared. And I treat this the exact same way as I would a normal degree 2. I need factors, things that multiply to 16, but add to, negative 16, but add to positive 6. And I know that the factors of 16 that are going to work for me is negative 2 times 8, because negative 2 times 8 is negative 16, but negative 2 plus 8 is positive 6. So using this, I can factor my expression. I can say this is x squared minus 2, and this is x squared plus 8. Set it equal to 0. Again, by the zero product property, the only way that this product will equal 0 is if each factor is set equal to 0. Doing so and solving, on the left-hand side, I would add 2 to both sides, so I get x squared equals 2. Taking the square root of both sides to solve for x alone, I get x is equal to plus or minus the square root of 2. X squared minus 8, x squared plus 8 equal to 0, subtracting 8 from both sides. You get x squared equals negative 8. Take the square root of both sides. You get x equals 2I radical 8. Remember, the negative can come outside as an I value, meaning it's a complex solution. And remember that 8 is 4 times 2, and 4 is 2 times 2. So this group of 2 escapes. So this really becomes, and this should have a plus or minus, I apologize, plus or minus 2I radical 2. Because this group of 2 breaks out, this group of 2 stays inside. So we end up with x is equal to plus or minus 2I rad 2, and x is equal to plus or minus 2. Now this is 2 solutions. This is 2 solutions from the plus and minus, plus and minus. So I have 4 solutions total. I always look at my degree. Was 4. So that means that I have found all of them. It's degree 4 because it's x to the 4th. We're going to do another example of a degree 4 polynomial. And I believe it's going to remind us about multiply, divide, slide. Okay, so we're going to do the same thing, but use multiply, divide, slide. We can still use that with degree 4 polynomials. So example 3 is going to solve by factoring 2x to the 4th minus 13x squared minus 24 is equal to 0. Now here, I cannot factor this very easily off the top of my head, so I'm actually going to use multiply, divide, slide strategy that we haven't used in quite a minute. So again, multiply the first and the last together. 2 times negative 24 is negative 48. Keep your middle term and change this to just x to the 4th. So I'm going to multiply, factor, divide, slide. This is the strategy I've multiplied. Now I need to factor this degree 4 polynomial, which was just like the last example. This is x squared, things that multiply to negative 48 but add to negative 13 are going to be negative 8 times positive 3. Negative 8 times positive 3 is negative 48, and negative 8 sorry, those are not the factors. Hold up. I apologize. Things that multiply, I was looking at a wrong step here. Things that multiply to negative 48 but add up to negative 13, I apologize, is negative 16 times 3. Negative 16 times 3 is negative 48, and negative 16 plus 3 is negative 13 squared. So to factor this, I'll use x squared minus 16, x squared plus 3. And remember, we still have this whole equation set equal to 0. So I've multiplied and factored. Now I've got to divide and slide. Since I divided or multiplied by 2, I'm going to divide by 2. I end up with x squared minus 8 times 2x squared plus 3. Since this does not divide nicely, it will slide in the front. So I've divided and slided and still have this quantity equal to 0. Since I'm solving by factoring by the zero product property, we will set each factor equal to 0. So we have x squared minus 8 equal to 0, and 2x squared plus 3 equal to 0. Adding 8 to both sides for this first one, I get x squared equals 8. taking the square root of both sides, I'm going to end up with x is equal to 2 radical 2. And the way I got that is, don't forget my plus or minus. 2 rad 2. Square root of 8 can be broken down to 2 times 2 times 2. One group of 2 breaks free, the other stays inside. Now I follow a pretty similar process for the second factor, 2x squared plus 3. Subtract 3 on both sides, I get 2x squared equals negative 3. Got to get x squared alone, so I get, divide both sides by 2, I get x squared equals negative 3 over 2. And again, I take the square root of both sides. Now what happens here is we get the square root of x squared is just x, but this radical becomes negative, the square root of negative 3 divided by the square root of 2. If you don't remember properties of radicals from Algebra 1, you can simply break up the radical on the top and the bottom. Now, the issue is we're not allowed to have a radical in the denominator, so we have to what is called rationalize the denominator. It's just not a nice approximation to have a radical in the denominator because it's irrational. And therefore, there can be, like in applied senses, there can be there can be rounding errors. So we need to rationalize our denominator, which just means we multiply by whatever radical is in the denominator. Doing so leaves us with x is equal to the square root. Negative 3 times 2 is negative 6 in the numerator. Square root of 2 times the square root of 2 just ends up with 2. And this will become, negative is going to become an I plus or minus I rad 6 over 2. I rad 6 over 2. Again, looking at my solutions, I have 2 here and 2 here, so I have 4 solutions total. 2 are real, 2 are imaginary or complex, and my degree polynomial that I started with was degree 4, since it was 2x to the 4th, so I know I have finished solving. Something you might start to notice is the degree of the polynomial is how many solutions we have maximum, and that is true. You might have all real solutions, you might have all complex, but at the end of the day, you will always be able to solve for exactly the number of solutions as the degree. And the last example of solving by factoring that we're going to do here, remember you can always pause if you need to as we're going through this. The last example of solving by factoring, example 4, before we move into dividing polynomials, is going to be 3x to the 4th minus 6x to the 3rd minus 5x squared plus 10x is equal to 0. And a strategy that we're going to use for this is called factoring by grouping. Factoring by grouping. Since it has 1, 2, 3, 4 terms, almost always when there's 4 terms, it's the easiest way to factor is by factoring by grouping. So how we do it is we're going to factor by grouping, and we basically cut the problem exactly in half. And what we do is we pull out the GCF of the left half and the GCF of the right. Our hope is that we have a common factor on both sides. So I like to cover it up and think of just the left half. right? When I'm going to factor by grouping, I'm focusing on just 1/2 at a time. So what is the GCF of 3x to the 4th minus 6x to the 3rd? Well, they both have 3 in common, so there's definitely going to be 3. And the greatest common factor in terms of x's is x to the 3rd, because I have x to the 4th and x to the 3rd here. So I'm going to pull out 3x to the 3rd. Doing so leaves behind the following. 3x to the 3rd times x is 3x to the 4th, and 3x to the 3rd times -2 gives me -6x to the 3rd. Now I repeat the process. On the right-hand side, I pull out the greatest common factor between -5x squared and 10x. So the greatest number they have in common is going to be -5. Always pull out the negative. The greatest x value they have in common is one single x. Doing so leaves me with -5x times x is -5x squared. -5x times -2 is positive 10x. And we've pulled out our greatest common factor. Still have our equations equal to 0. So when you factor by grouping, what you should end up with is 2 factors on either side that are exactly the same, a perfect match. And in this case, it's x minus 2. So we keep our perfect match as x minus 2. And what happens with the other 2 greatest common factors is they go into their own factor together. So I'm going to drop them in. It could be on the left or on the right, it doesn't matter. 3x to the 3rd minus 5x. So it's like we're factoring out the greatest common factor right here, which is why we have x minus 2. And now I have this entire equation equal to 0. So factor by grouping, you cut it in half, factor out the GCF on both sides. You should have a perfect match. You write that one time. The GCFs from each side go together in their own factor pair, and we have it set equal to 0. Now we're almost done, except I happen to notice that 3x to the 3rd minus 5x also has a GCF. It's not always the case, but I notice that they both have x values. So I'm going to factor out an x. Doing so leaves 3x squared minus 5. And we still have x minus 2. Set it equal to 0. Now I have something times something times something equals 0. Again, this is going to be using by the zero product property. This can only happen if each factor is equal to 0. So x equals 0 is the first one, pretty quick. 3x squared minus 5 is equal to 0 is the next one we're going to solve. And x minus 2 is equal to 0. Got the first one, lickety split, super quick, right? The second one, if I need to solve for x, I have to add 5 to both sides. I have 3x squared equals positive 5. Must divide by 3 on both sides. I have x squared equals 5/3. I would want to take the square root of both sides, leaving me with x is equal to the square root of 5 over the square root of 3. I'm not allowed to have radicals in the denominator, so I must rationalize. Multiply by root 3 over 3, because that's technically 1. I end up with x is equal to the square root of 15 over 3. And I forgot my plus and minus. So plus and minus. So I found 1 root, 2, 3 roots. This one is 2 here. And the last one, x plus 2 equal to 0. Add 2 to both sides, you get x equals 2. And that is my 4th root. again, this is one solution, two solutions, one solutions, 1 plus 2 plus 1 is 4 total solutions. And I have a degree 4 polynomial, so I know I am done. 3x to the 4th, degree 4, I can have maximum 4 solutions. And they all happen to be real in this instance. So my polynomial will cross the x-axis 1, 2, 3, 4 times. So now we're going to get into dividing polynomials, and I'm actually going to put that into another video. So I'm going to stop this here, and we will talk about dividing polynomials in the next video.